All right, good afternoon, and thanks. This is that's quite a responsibility to be the last talk in the day. I should say, I think my talk is a little different. First of all, it's, I don't know, I think it's the 10th talk today, and it's the first one on neutral atom platform, which is, I think, a first for me. Second, I am not a priori zooming in on QuDits, but you will see that QuDits actually play a role. It is also actually really based only on one piece of work, which is a little bit kind of a stack of co-design and how do we design our system and how do we measure it and how do we ask the question, etc. So this is what this is all about. Okay, so as I say, this is based on this paper which was submitted by a good half year ago. And here is all my courses, and I would like to highlight in particular Nishat and Stefan, who really did all the heavy lifting, and Anna and Martin Head-Gordon, Anna Krylov and Martin Head-Gordon, who are actually chemists. So I should really say that getting to this work, getting to really ask the question, work on this, etc., meant kind of understanding what are the questions that quantum chemists really ask. And this probably took by far the longest part of the work. And Anna and Martin helped us with that. Okay, so what is quantum chemistry? Quantum chemistry means solving electronic structure problem for configuration of electrons and nuclei, which for physicists basically means dealing with this Coulomb type Hamiltonian. Let me tell you, for a serious size molecule, nobody can solve this exactly, but people try. This is in general challenging. In particular, it's challenging if we have strong correlation, and because of the unfavorable Hilbert space, this came up a couple of times today, that is where it might be possible that quantum computers come in useful. I like to kind of first go back to this by now already somewhat semi-old Microsoft paper, who kind of make a list of the most important quantum algorithms, dynamics, factoring, quantum chemistry, in a grid which has the physical qubits in millions on the y-axis and the runtime in seconds on the x-axis. Here is these different symbols means a little bit different properties. So we have gate times between microseconds and nanoseconds, and we have errors between 10 to the minus 3 and 10 to the minus 4. And if you look where quantum chemistry is located, it doesn't look so good. So it needs close to 10 million of physical qubits. Well, I mean, people can do more than 1,000. So this is perhaps, one can imagine to reach that. But imagine you have already this nanosecond to microsecond, really pretty good gates. Then a single quantum chemistry calculation on a quantum computer that is built already and you have available takes somewhere between a month and a century, if you use the algorithms that are known to be useful for quantum chemistry right now. So that does not sound so promising. So it might be useful to kind of find other ways. So first of all, why is that so hard? The first is the mapping of the target problem to the quantum hardware is very non-trivial. And I'm not talking a lot about that, but I think that's one of the problems that right now really kind of drives me. The second is that these quantum chemistry algorithms are based on kind of expensive building blocks like quantum phase estimation, and then there's of course quantum error correction. And so what we are trying to do in this work, and we are kind of widening this, but for right now, is trying to see how far can we get into this quantum chemistry problem answering if we are actually doing quantum dynamics. Okay, and so what we want to do is we want to simulate relative quantum dynamics on near-term hardware. So our approach is to leverage the insights that the quantum chemists have already. We are not reinventing the wheel. Second, use state-of-the-art quantum computer. In our case, that's our so-called programmable quantum simulators. And the third one is focus on hardware-efficient implementations. And this is also where this QuDits thing and so on comes in. And again, we are right now concentrating on problems with strong correlations. And here is our workflow. So in particular, this is hybrid. First of all, we do use quite a bit of classical calculation, and we do employ state-of-the-art algorithms such as coupled cluster and DMRG, and this is done in quantum chemistry already. The second thing is also already there. This is building so-called model Hamiltonians. There is a whole kind of art and science to this, but you can imagine that as taking the pieces that are already known in quantum chemistry, namely, for example, well-known functional groups or something like that, packing them all together in one logical node, and building a model Hamiltonian that consists only of these logical nodes. And therefore, quite considerably kind of simplifying the problem by using a lot of the stuff that is known very well already. And in our particular case, these model Hamiltonians are supposed to capture the strong correlations. And in particular, we want to do that at low energies because that is what's important for chemistry. Please do note, we are not just interested in ground state energies. We are interested in the full kind of low energy manifold. And then, of course, the new part is to do the quantum computer, and this is what this work is really about. And at the end, we use all three of them together. So here again is this model Hamiltonian, and in our case, as you can see, we really simplify this a priori really big question rather considerably. Namely, we say, okay, a priori, one of the strongest correlation is if we have a system that has a lot of large spins. So our spin is S, and this is for all what I'm talking about. If I use a capital S, that typically means the spin that is larger than 1/2. And therefore, by definition, a QuDit, right? So the second thing is that we kind of then limit ourselves to spin Hamiltonians. They are actually rather relevant for a lot of the chemistry that people do. But in terms of spin Hamiltonians, we don't a priori limit ourselves further. We look at single spin, 2 spin, but also higher 3 spin, 4 spin, etc. terms. And we don't a priori only kind of look at any kind of symmetric interaction terms, J and K and so on. Okay, so here is an example molecule that kind of embodies all of what we want to do. This is a very good model for materials or molecules in this case, for which a model Hamiltonian exists. The quantum chemists have worked on this already. And this is a good example because it is easy to obtain as a model Hamiltonian, but it's very difficult to solve. So this is where we can basically come in with our quantum computer. The second thing is that this high spin in principle gives a more natural mapping to quantum hardware, which basically, of course, also answers one of those questions that's central to these workshops. Why do we actually need QuDits, right? That is one very obvious example. Here are some. Okay. This particular molecule is actually a biochemical catalyst, which is part of the oxygen-involving complex in photosynthesis. So this is actually a very important real-life molecule. Why is that interesting for us? As you can see, and this is actually, this is kind of simplified. There's, of course, a lot of functional groups everywhere, the edges, etc., which are left out of this picture. But in particular, this molecule has 4 manganese atoms. So manganese is one of those transition metals which has 7 valence electrons. And of those 7 valence electrons, some of them are used for this kind of coherent, covalent bonds that you can see here. And in particular, this manganese of the so-called oxidation state 4, that means 4 of these electrons, valence electrons, are used for covalent bonds, which means that we have 3 left over that are active. And these 3, they act as a spin 3/2. So this is where these high spins come. And basically all of these transition metal parts of catalyst molecules or other kind of biochemically important molecules have a structure that is similar to this. And as you can see, we have 3 of these manganese have oxidation state 4, and 1 actually has 3. So we have 3 3/2 spin manganese and 1 spin 2 manganese. And here there are basically 3 different interactions. The one is the Coulomb interaction, which localizes the electrons. And that one is basically solved, not 100%, but approximately with what people have done with the typical structure calculation so far. But the spins are involved both in exchange interaction, super exchange interaction. And the exchange interaction are ferromagnetic in type, and the super exchange interaction are anti-ferromagnetic in type. And so in general, if we have a system like that, we have a frustrated system, which is a priori not easy to solve. And what the quantum chemists do is building this model Hamiltonian, which then kind of simplifies this whole molecule to something like this. And please do note, that looks pretty simple. But this whole thing gives a Hilbert space scaling of 2s plus 1 to the n, where s is the spin, n is the number of those molecules. This is 4, so in our case, this would be 2 orders of magnitude. And this scaling comes on top of what the quantum chemists have to do already without those high spins. And so that's why it's hard for them, because they are basically already more or less at the limit what they can do, and suddenly we ask them to kind of do a factor of 100 more. So this is why this is a hard problem. So this is at least kind of a rough idea of that. Okay, so there are 3 challenges in this problem. The first is how to represent the high spins. So QuDits, but we don't have QuDits, we have Rydberg atoms. The second, how can they interact? Because we need non-local connectivity for this problem. And the third one is how can we actually read out chemically relevant quantities? And for that, we use some heavy quantum classical coprocessing. I will give you a little bit of an idea how that goes. Here are these 3 things. I want to go, this non-local connectivity is kind of the meat of the matter, and I will go very short on this because this is not really my work, and it's it has nothing to do with QuDits. But the idea is that we have this Rydberg arrays with very good gates, and you can basically forget about this upper level, except that we have these arrays of atoms, and that the gates are based on the so-called Rydberg blockade. Just very briefly, the Rydberg blockade, the idea is that Rydberg atoms interact extremely strongly on the order of magnitude, on the order of something like 10 millimeter distances or something like that. And ground states, and on that distance, they don't see each other. So that means if you have 2 atoms, which are either in the ground or in the Rydberg state, if you send one resonant photon in, you get some superposition of Rydberg ground and ground Rydberg. If you send a second photon in, then in principle, you get a double Rydberg state. But if you have the atoms so close together that they start interacting, this is a 1/6 type interaction, so if that kicks in, then this double Rydberg state goes strongly out of resonance, and your two atoms, your two photons don't do anything. So that means if you have these two atoms so close together, you can excite only one into the Rydberg state, but not two. And of course, and this is why this is also a great gate for anything more than a qubit, you can have, this doesn't only work for two. If you have three that are close together or four that are close together or so, you still can excite only one. And this can be built into a nonlinear gate, and I'm not going into detail how that works, but what I should say, it's very robust because you just have to have them close enough together. It doesn't matter how close they are exactly. The second element in this Rydberg arrays is that you have these atoms that can be put in the Rydberg state, but that you also can move around while the computation is going without losing your coherence. And that gives us, of course, a non-local connectivity. And here's a little bit a kind of couple of figures of merit about how good the gates are, etc. So we have a high degree of programmability. We have the interactions that are manipulated just via this geometric configuration. And we have global control pulses. So we have pulses in a similar manner as we have heard a couple of times today, but they are always global. So whatever you shine in there, you shine on all of them, all of the atoms. So this is basically the first is non-local connectivity. So now we come to the high spin. That's basically the central part. And our QuDits are very trivially just a couple of qubits put together. This is a little bit anticlimactic compared to what we have heard so far. And there are, in principle, for Rydberg atoms, much better ideas, like some of what, for example, we have heard about ions today, where you just use several internal states that you then address separately. Of course, for Rydberg states, we have the same capabilities. But the experiment right now cannot do that yet. So if we want to implement that, qubits it is. So our high spins, we just say any spin S variable we encode into 2S qubits. We call this a cluster. And these clusters we can a priori assume to be within one Rydberg radius. So Rydberg radius is the radius below which we have this blockade that I just explained to you. And each of those qubits is encoded in the 0 and the 1 in a ground state, which are coupled time dependently if we want. And then we have the Rydberg state, which is coupled only to the 1. And these two fields allow us to put pulses in. And in principle, this is a good idea, but we also heard it today, because not every state of 2S qubits is also an S spin state. Only the symmetric manifolds are actually valid spin S states. So the thing is, we have to make sure that we are always kind of getting back into this correct manifold in order to kind of be in the right state. And the idea is we engineer two-field pulses out of these two fields using the Rydberg blockade, and we can actually implement any 2S qubit gate of the qubits that sit in here. And here are two examples of gates that are very important. The one is an all-to-all interaction, Heisenberg type. And the second one is the projection that always projects back into the symmetric substates to make sure that we stay in our spin S state. And then we also use great pulses. We have seen that a couple of times today. So the pulses, they might look something like that, and this has been used a lot. I don't need to tell it to this audience. And here is a comparison between these multi-qubit gates and 2-qubit gates. And please do note, and you will also see that, what I call multi-qubit gates are now 2 QuDit gates, really. okay? Well, no, it's not quite true. Right now, it's one qubit gate. So far, I've shown you only one qubit gates. The two qubit gates come soon. So here, we have these two example operations that I've just showed you. And this here is the gate time that the pulse needs in order to make these two gates for 2, 3, etc., all the way up to 8 qubits. And you should look at this lower line. This is if you optimize the pulses at the same time. And the nice thing here is what we see, and this is perhaps also a little bit similar to what Martin has told before, is that here this gate time basically doesn't go up if we have more qubits in there. So we can as well do kind of, spin 3½ as spin 5½ as we can do spin 1/2. Of course, if we kind of encode that in 2-qubit operations, here we have to count gates rather than gate times, but it's nevertheless a reasonable comparison. We see that for the same number of qubits, this basically increases exponentially. So at this point, we have already an order of magnitude speed up for our system. Okay. Everything else is basically really very much geared towards the quantum chemistry. So here is, let's take a target Hamiltonian. Here for simplicity, we take only a 2-qubit Hamiltonian, a 2-spin Hamiltonian. And here, just in my little example here, here's a spin 3½ a spin 2, a spin 3½ here's a spin 1, etc., and we have 16 of them in total, just for illustration. And this target Hamiltonian does not need to be one of those typical kind of Hamiltonians that we use, for example, in condensed matter. Or so, for example, we can have a connection that is a kind of combination of Heisenberg and antisymmetric Jalushinsky-Maria, or it can be kind of completely arbitrary. So how does that work? So here's our target Hamiltonian. So the first thing is we configure our system such that we take one qubit out of each spin cluster to have it interact with all of the other kind of clusters that we need. Ideally, we can do that all in parallel. If not, then we have to do it in several steps. Then we run a 2-qubit gate on all of these. This 2-qubit gate encodes exactly this target Hamiltonian, except that here these are the spin s, whereas here these are the qubits. So what we have all the full functionality, but only for the spin 1/2, which of course now violates this large spin encoding. So we have to get that one back. So we reconfigure back into our clusters and make this intra-cluster gate, which is this projection into the symmetric subspace. And in order to do that all right, we kind of have to do this program basically in a Floquet type repetition of this. And so what we get at the end is an effective evolution operator of k steps where we alternatively use the intra and the cluster Hamiltonian. This can be part of that, can be large angle rotations, but I'm not going into depth on that. And the thing is, if you do a Floquet type engineering, you can either cancel out the higher orders, that is what you would need to do for the Hamiltonian that I just showed, or we can even say we want the higher orders and control them via Floquet engineering. We can, of course, also have this higher order if we now go back and instead of taking one atom out of 2 clusters and let those 2 interact, if we want to interact 3, we take 1 out of 3 clusters and let the 3 interact. So we have really seriously multi-qubit gates, which then translate into multi-qudit gates. Okay. So this is basically this high spin control. which can be done. So the kind of the target that we had for those pulses was a 0.1% error, just to say that. So now with the last kind of, I don't know, 5 minutes or so, I explain you how we do the readout, which needs some heavy classical calculation. So what we do, we leverage the ability for this efficient time evolution, and we use also the fact that we can make snapshot measurements. That's something that is, I wouldn't say unique to the Rydberg, but it is very helpful that one can basically, with a single camera click, capture the whole array in one shot. Of course, you measure in the measurement basis in this case, and that you can do for different preparation, different evolution times, etc. And this whole kind of set of data is very information dense. So it is a little bit reminiscent of this kind of shadow tomography. But the thing is that we kind of have come up with a way how to kind of make the most of this information that we have gathered at that time. And the way how to do that is by defining a new quantity, which we call operator resolved density of states. So this depends on an operator A. Just assume for a second that this is just the unit operator, okay? Then what you can see is that this quantity is basically just a spectrum. But if A is something different, we can highlight basically different physical properties depending on what we choose for A. So this is that. So why is that a useful quantity and how do we get it? And this is basically a couple questions. The reason why this is such a nice quantity, and I show you some spectra afterwards, that we can actually calculate this efficiently. And the calculation first is based on the fact that this is an average over different evolution time, over different state sample, and over different observables. And each of them consists of a classical correlation, which is basically the time evolution of a known reference state, which therefore can be calculated very efficiently classical, and the time evolution of an unknown superposition state, which we need to do on a quantum computer. And this is really what we need the quantum computer for. This is this step here. And here is some more details, which sorry, the last thing I do want to show you. The thing is, we can use the same data for any kind of number of different operators A. And here is a cartoon of our circuit. So what we have, we start with, for example, everything in the 0 or so. Then we start with a reference state which is easy to prepare. And what is easy to prepare depends on the system. Then we make a controlled hour, so a controlled disturbance, and we sample over different hours. And after that, we run our time evolution. This is the Floquet evolution that we have. And then we make this snapshot measurements, and this gives us 2 to the n observables, where n is the number of qubits. And here is a simple example where we calculate this for just 2 interacting spins we have, a Heisenberg of that. This is running 20, or actually simulating in this case, 20,000 samples. And the spectrum, when A is unity, is just this black line here, whereas these gray lines are it's the solution from exact diagonalization, which for such a small system, of course, is very simple. So because the quantum computer is not perfect, and we built that into our simulation, we get the finite widths of these peaks. And we also see that for this spectrum, we actually lose this lowest energy level here, right? So that's basically, if you would make a spectrum experimentally, that's what you would expect to see. if your resolution is not very high. So, but then, without taking any more measurements or anything like that, we replace A with the projector into either the total spin 3 state, the total spin 2 state, etc., which gives these colored lines. And we find that the total spin 0 state gives actually the slowest spectral peak, the total spin 1 state, the next spectral peak, etc. And we can now get extremely good resolution without kind of changing anything about our data taking or the errors of the system or anything like that. If we take a different kind of operator A, so here the operator A is just a sigma z, we can take, for example, either 10K or 50K measurements and kind of put the solutions into a Boltzmann distribution and get the susceptibility of the system over temperature. And here you see how the errors roughly go. So 10K is not very perfect, 50K is already pretty good. And now, of course, we have to do the same thing for our real molecule. And what we find here is a spectrum that looks something like that. But we are, as I said, mostly interested in the low energy manifold. And so we kind of zoom in on that. And we find, again, this black line is what we get from the unit operator. And if we kind of zoom into these different spin manifolds, we kind of get really good resolution. For example, if you see this we can resolve now this yellow line and the red line. And in this particular case, this is down to 0.3 wave numbers. And in particular, here we can make some comparison of two different possible kind of configurations of this whole molecules with experimental data. And this allows us to actually say, okay, the correct kind of spin structure is this kind of manifold, this first manifold. Okay, so this kind of gives you a little bit of an idea, and I'm actually out of time. So I'm just showing you that we also can do condensed matter, which I'm not showing you. Here's a couple of next steps. Namely, this operator resolved density of states, something we heavily work on right now, and we have a lot of ideas. How to include error correction in general in systems like that is a big open question. Dynamics of chemical reaction is actually not that hard, because if one knows the low-level spectrum, that's relatively simple. But one of the big questions is now how to go from spin to fermions. And we have some more results, but I'm not going to show this, and I want to thank you.